The modern nuclear submarine operates as a high-stakes, heavily isolated edge computing node, processing massive environmental datasets. Look at this split-screen comparison. On land or in space, radar and light travel in straight lines, but underwater, as we see on the bottom, acoustic waves warp, bend, and fracture when they hit varying horizontal water layers. Because of this non-linear refraction, a crew has to constantly calculate exactly how sound is bending around their hull in real time. In the deep ocean, stealth is a mathematical output. You have to transform the surrounding water into a queryable grid to know exactly who can hear you. To solve this massive computational problem, the U.S. Navy developed two interconnected systems, MOODS and DBDB. These are foundational environmental intelligence databases. Together, they map the acoustic physics of the entire global ocean. Without this localized data to model the ocean's non-uniform properties, a submarine running dead silent is still highly vulnerable to a single ping of active sonar. To understand how these databases work, we have to look at the physical variables that control the sound speed profile in water: temperature, pressure, and salinity. When an acoustic wave hits a pocket of water that is noticeably warmer, deeper, or saltier, its velocity increases, causing the wave path to physically bend away from the change. A thermocline is a sharp boundary where warm water sits on dense, cold water. Sound hitting it from above sharply refracts upward, unable to penetrate below. This creates a massive dark void underneath, forming a shadow zone. These zones are invisible, entirely made of sound, and they shift constantly. Mapping them on a global scale is a strict prerequisite for keeping a crew alive. The Navy tracks the water column using the Master Oceanographic Observation Dataset, known as MOODS. MOODS structures the ocean as a 4D data cube, mapping latitude, longitude, depth, and time for seasonal variations. Inside each grid cell, it stores historical profiles of temperature, salinity, density, and sound speed. An onboard combat system queries this vast array, pulling localized sound speed variables for a specific coordinate and season to understand the surrounding water. While MOODS maps the water, a second system maps the physical container holding it. Enter the Digital Bathymetric Data Base, or DBDB. DBDB is a high-resolution 3D physical boundary layer, tracking the terrain of the seafloor. This mesh highlights deep trenches, underwater canyons, and continental shelves. The acoustic relevance of this terrain is immense. DBDB stores detailed sediment type layers and bottom loss coefficients, allowing the combat system to calculate exactly how much sound energy will be absorbed or reflected by the ocean floor. Together, MOODS and DBDB form a complete digital twin of the ocean's precise acoustic properties. Populating this digital twin relies on aggregating environmental intelligence from every ocean basin. The Navy pulls raw environmental telemetry from a multi-domain network, including satellite altimetry, Argo floats drifting on currents, and classified undersea sensors. They also rely on physical hydrographic surveys. Oceanographic research vessels like the USNS Bowditch operate constantly at sea, taking direct measurements of the deep ocean. All of this disparate oceanic telemetry is collected. The raw data is cleaned, gridded, and interpolated into a standardized mathematical format. Once compiled, the finalized dataset is heavily compressed, indexed, and version-controlled for deployment to the fleet. This pipeline translates billions of scattered physical measurements into a single cohesive spatial map, ready for active military distribution. Deploying this data reveals a severe hardware constraint. Submarines operate completely offline, with zero cloud connectivity. To compensate, each boat carries a massive local cache of the MOODS and DBDB databases, stored on its own internal server racks. The database is updated through an asynchronous pipeline, relying on secure data cartridges and fiber optic uplinks whenever the submarine is docked in port. While underway, the database can receive critical seasonal updates via highly compressed satellite burst transmissions, ensuring the local model remains accurate. The submarine's combat system, known as BSY-1, ingests the raw water column data from MOODS and the physical boundaries from DBDB to run real-time physics simulations. The system uses heavy compute mathematical models, deploying ray trace solvers, parabolic equations, and normal mode propagation calculations. These solvers output a predictive topological map showing exactly how far enemy sonar will reach. mapping out torpedo guidance envelopes, and calculating safe depth limits. The onboard processing turns massive amounts of passive stored data into a real-time, physics-driven tactical envelope. Consider a high-stakes scenario. A submarine detects an active sonar threat and must use its database to vanish. Look at this split rendering. On the left, the onboard database runs a finite difference grid to compute a thermocline's precise depth and refraction angle. On the right, the combat system translates that math into a physical boundary. Armed with this calculation, the crew deliberately maneuvers the vessel into the calculated shadow zone, placing themselves just beneath the warm water layer. When the enemy's active sonar pulse sweeps the area, it hits the top of the thermocline and physically refracts upward, leaving the submarine completely undetected in the void below. Perfect evasion under pressure is not an instinct. It is the direct result of the MOODS database executing a precise, real-time computation of the water column. When localized MOODS or DBDB data is outdated, the predictive models used for sonar and navigation fail to match physical reality. An inaccurate environmental model causes the onboard acoustic predictions to collapse. Torpedoes will lose lock, and calculated shadow zones will instantly vanish. Inaccurate data creates a high risk of detection, forcing the vessel into a state where it is fully visible to enemy sonar or physically exposed at the surface. These databases provide the environmental logic required for the silent service to operate. Modern submarine stealth relies entirely on a global enterprise data architecture that continuously computes a mathematical map of the deep.